Welcome to video 1 on section 11.6, where we're going to learn how to solve systems of equations using Gaussian elimination. So the learning objectives for this video are to learn how to perform row operations on a matrix, how to write an augmented matrix for a system of equations. I feel like those are the same things. Write the system of equations from go back and forth between an augmented matrix and a system of equations. Sorry, my brain stopped there for a second. Use a computer to perform row operations on a matrix, and also use yourself to perform row operations on a matrix, and solve a system of linear equations using matrices both by hand and using a matrix calculator. All right, so let's talk about systems of equations as matrices. So we can use matrices as a shorter way or a shorthand way to write systems of equations. So let's go ahead and practice with this system of 3 equations and 3 unknowns. If we're going to use a coefficient matrix, we're just going to write in the left-hand side. That's the side with all the coefficients on the variables. And what we're going to do, oops, that doesn't have a pen associated with it. We're going to write this as a 3 by 3 matrix because each variable has 3 coefficients, and there are 3 variables. So this matrix is going to be 3 by 3. 3 variables, 3 coefficients. And I'm going to write the coefficients on x in the first column, so that's 1, 4, and -1. I'm going to write the coefficients for y in the second column, -1, 7, 5, and the coefficients for z in the third column. Oops, 2, 1, and there is no coefficient, so I'm going to use a 0 as a placeholder. Right? That's called the coefficient matrix. An augmented matrix, which is what we're going to use, has a vertical bar separating the columns of the matrix into 2 groups, the coefficients on the left-hand side and the solutions on the right. So the first bit of the augmented matrix is going to be the same, 1, 4, -1, -1, 7, 5, 2, 1, 0. Then I draw a vertical bar, and then I put the left-hand side, or the right-hand side of the value. So 5, 1, 4. And this is my augmented matrix, and this is mostly what we're going to be working with. I just wanted to show you what a coefficient matrix was. So you can see this part right here is your right-hand side of your equations. All right, let's go ahead and practice this. I would like you to go ahead and look at this example and write the coefficient, and actually just go ahead and write the augmented matrix. Just write the augmented matrix down for the following system. So pause the video and write down your augmented matrix. All right, so we're going to write the coefficients on x first, 4 and 3. The coefficients on y, -3 and 2, our bar, and then 11 and 4. Let's try going back the other way. I would like you to write the original system of equations that would have produced this augmented matrix. Go ahead and pause the video and write the original system of equations for this augmented matrix. All right, well, there's a couple ways to do this. I'm just going to write 1x, 2x, 1x, plus 2y, plus -y, plus -3y, minus z, plus 2z, plus 3z, equals 3, 6, 4. So you can go back and forth between those. All right, we're going to try to learn how to solve a system equation by using matrix operations. Our goal is to take a matrix that is all full of numbers and make it look like this. Before I tell you, this is a matrix and it's in reduced echelon form. Before I even talk about how to get it in that form or why, what we have to do to make a matrix look like that, let's talk about why we want that. And the way we're going to talk about that is we're going to look at this augmented matrix that is in that form. So you can see there's ones on the diagonal. There should be a little line here, but I'm pretty bad at putting those in the word. There's ones along our diagonal. All right, so we can see the ones. There's zeros below, and there's numbers everywhere else. Well, to see why this is a useful thing, let's go ahead and translate this back into a system of equations. All right, so it tells me that x and then 0, 0 plus 2y plus y plus 2z plus 2z plus z equals 13 equals 12 equals 5. And if you like to do that left to right, that's totally fine too. So x plus 2y plus 2z is 13, y plus 2z is 12, z is equal to 5. Do you recognize this form of a system of equations? This is triangular form. And it's almost solved, right? We can finish solving this no problem. We know that z equals 5. We use that here to say that y plus 2 times, which we know is 5, is equal to 12. Y plus 10 is 12, so y is 2. And finally, x plus 2 times 2 plus 2 times z is 5 equals 13. So this is all stuff we learned how to do when we solved systems of equations. So that means x must be -1. So if we can get an augmented matrix into this form with the ones on the diagonal and the zeros, we can translate it back into a system of equations and easily solve it because it's in triangular form. Right? So that's the plan. How do we get to the plan? Well, first thing we need to learn how to do is how to manipulate matrices. How do we get the matrix from looking like a whole bunch of numbers to getting into this reduced echelon form? And the answer to that question is row operations. So let's talk about row operations, and that will be where we stop this first video. So what are our 4 row operations? Well, what we can do is we can interchange any 2 rows. We can multiply any row by a constant. We can add rows together. And we can multiply one y by a constant and add it to another row. I'm going to do these examples in both in the systems of equations notation and the matrix equation to kind of encourage you to believe that these are all legit things we can do to linear equations. So interchange 2 rows. If we did this with the systems of equations, and here's just an example system, we would just write the first row as 3x plus 2y equals 4, and the second equation as 4x minus 3y equals 11. And I think you guys would all feel very comfortable in saying that's still the same system of equations. What it looks like in matrix notation, in matrix row operations, would be taking that 3, 2, 4 row and putting that in row 1, putting 4, negative 3, 11 in row 2. So really that's the same process of just switching the order of your equations. It's still the same system. Multiply a row by a constant. Well, remember when we did elimination with our systems of equations? Lots of times we would multiply a row by a constant, especially if we wanted to add it to another row. So let's just multiply row 1 by 2. So that would be 6x plus 4y equals 8. This is still the same equation, going to produce the same solutions as 3x plus 2y equals 4. This one was left alone. In our matrix, this would be the same as taking that row and multiplying row 1 by 2 would be 6, 4, 8, 4, negative 3, 11. And actually, maybe I should have done this with our original matrix, but whatever. All right, adding 2 rows together. We do this all the time. We add rows together and replace the row with it. So for a linear system of equations, maybe we add row 1 to row 2 and replace row 2 with it, right? Row 1 plus row 2 replaces row 2. So that would be 4x minus 3y equals 11. I'm going back to the original one. Let's go from the original. Add them together. That would be 7x plus minus y equals 15. So that's just adding these 2 equations together to form a third equation. Still legit in our systems of equations, legit with matrices. Let's go back. So our row 1 is 4, negative 3, 11. And our new row 2 would be 7. Negative 3 plus 1 is negative 1. 11 plus 4 is 15. So you can see what we're doing with the matrices when we're doing these row operations. We're just kind of keeping track of our constants, our coefficients in our systems of linear equations. And it's just a more convenient way of keeping track of our coefficients than having to write the x and the y and the equals all the time. It just takes that part away and just worries about what the coefficients are doing. And finally, multiply one row by a constant and add it to another row. This was a big step in elimination, right? That was the whole point of getting rid of something. So let's go ahead and multiply row 1. Let's see if we can get rid of this 3x. What would we do if we're doing elimination? Well, we would multiply row 1 by negative 3/4, right? Times row 1, add it to row 2, and replace row 2 with that. All right, well, maybe you should have done that before, but whatever. So negative 3/4 times row 1 would be negative 3/4 times x is negative 3x plus negative 3/4 times negative 3 is 9/4 y equals negative 3/4 times 11 is negative 33/4. And now we're going to add this to row 2. So this guy is still the same. Adding to row 2, we get 0x, so that's gone. 2 is the same as 8/4, so we have 17/4 y equals negative 3 over 44 plus 6, negative 33 over 4 plus 16 over 4 is that 17 over 4? Yeah, 17 over 4. All right. So there's our new system. We can do the same thing with matrix part. So we're going to multiply row 1 by 3/4, and that's going to give us 3/4 times 4 is negative 3. Negative 3/4 times negative 3 is negative 9/4, negative 33/4. And when we add down, our matrix will be 4, negative 3, 11, 0, 17/4, 17/4. All right, so you can do the same things that you did in the process of elimination. And in fact, elimination is just kind of easing you into matrices that you can do in matrices.